Hello friends, I welcome you in lecture number 44 on Laplace Transform. In this lecture, we are going to discuss about integral equations. We will see the meaning of integral equations and we will discuss how to solve integral equations of certain type using Laplace Transform. So first we understand the definition of integral equation. An equation in which the unknown function y of t appears under the integral sign is known as integral equation. For example, you can see this equation y of t equal to t plus integral from 0 to t y of u sine of t minus u du. So here y is unknown function of this equation and it appears under this integral sign. So this is an example of integral equation. Convolution helps in solving certain integral equations. We have discussed about convolution theorem that we are going to use in solving integral equations. But we cannot solve integral equations of all types using convolution theorem, but we can solve those type of integral equations in which we are able to represent integral in the form of convolution. And we know the definition of convolution. If we have two functions f and g, then we can write convolution of f and g as integral from 0 to t f of u g of t minus u du. So integral equation in which we are able to write our integral in terms of convolution, those type of integral equations we can solve using convolution theorem. So we understand this solution of integral equation with the help of this example. Solve the integral equation y of t equal to t plus integral from 0 to t y of u sine of t minus u du using Laplace transform. Here we are interested in the value of unknown function y which satisfies this integral equation, and for that we are going to use the concept of convolution theorem. First we write down the given equation or given integral equation. It is y of t equal to t plus integral from 0 to t y of u sine of t minus u du. Now if we want to apply convolution theorem, we should try to write this integral in terms of convolution. For example, if you consider the definition of convolution, if you compare this integral with the convolution definition of convolution is 0 to t f of u g of t minus u du. So you can compare these two integrals. You may have the idea that we might be able to write this in terms of convolution of these two functions f and g. So how to decide that which function we have to consider as f and which function we have to consider as g? So that you can compare. You can see in this we are having variable u and here we are having t minus u. So from this we may have the idea that we should consider function f as unknown function y and we should consider function g as sine function. Suppose I consider f of t equal to y of t, then f of u will be equal to y of u. And if I consider g of t equal to sine t, then this is going to be sine of t minus u will be equal to g of t minus u. So from this we may have the idea that we are able to write this integral as the convolution of two functions. Here those two functions are y and sine t. So we can directly write that this is nothing but convolution of function y and function sine t. and we can mention in the bracket also that we are using this definition. By the definition of convolution, y star sin t equal to integral from 0 to t y of u sin of t minus u du. So this is first step, express integral of integral equation in terms of convolution. In the next step, we will consider Laplace transform on both sides of this equation. Therefore, Laplace transform of left hand side, that is y of t, equal to Laplace transform of t plus y star sin t, and by the linearity property we can write directly that this is equal to Laplace transform of t plus Laplace transform of y star sin t, and we use the notation y bar s for the Laplace transform of y, and Laplace transform of t is 1 divided by s square. We know the formula for Laplace transform of t raised to n. If n is natural number, it is n factorial divided by s raised to n plus 1, and here power is 1, so we have 1 factorial divided by s square. And by the convolution theorem, Laplace transform of y star sin t can be written as product of Laplace transform of y and Laplace transform of sin t. Here we are using convolution theorem for Laplace transform. So here we write that this is by convolution theorem. Now in the next step, we write down Laplace transforms of these two, and other things remains as it is, 1 by s square. Y is unknown function, and Laplace transform of y is denoted by y bar, and Laplace transform of sin t is 1 divided by s square plus 1. Our aim is to decide y of t, unknown function y of t we must find. So for that we first find out y bar. So this I can rewrite as y bar s equal to 1 by s square plus y bar s divided by s square plus 1, and I am interested in y bar s. Therefore I consider this on left hand side, y bar s minus y bar s divided by s square plus 1. This is equal to 1 divided by s square, and we take y bar s common from these two terms, and we have 1 minus 1 divided by s square plus 1, y bar s equal to 1 divided by s square, and we simplify this. This is s square plus 1 minus 1 divided by s square plus 1 into y bar s equal to 1 divided by s square, and this is s square divided by s square plus 1 into y bar s equal to 1 divided by s square, and our aim is to decide y bar s. So we rewrite again, we consider this function on this side, so it is s square plus 1 divided by s square. Therefore y bar s equal to s square plus 1 divided by s to the power 4. Again we rewrite this. Therefore y bar s equal to s square divided by s raised to 4, that is 1 by s square plus 1 divided by s raised to 4. Now we take inverse Laplace transform on both sides, and we have ready-made formula for the inverse Laplace transform of 1 divided by s raised to n. So we will use that formula. First we use the linearity property, and we can write in this way: inverse Laplace transform of this plus this equal to inverse Laplace transform of 1 by s square plus inverse Laplace transform of 1 by s raised to 4. Now we recall the formula for the inverse Laplace transform of 1 by s raised to n. It is nothing but t raised to n minus 1 divided by n minus 1 factorial if power is natural number. And the left hand side is inverse Laplace transform of y bar s, which is y of t, and here n is 2, so this is going to be t raised to 2 minus 1, that is t, divided by 1 factorial, that is t, plus here t raised to 4 minus 1, that is 3, divided by 4 minus 1 factorial, that is 3 factorial. And finally we obtain our unknown function y as t plus t to the power 3 divided by 3 factorial, which is, so in this way we can solve this type of integral equations using Laplace transform. So we just summarize all the steps. First we write this integral in terms of convolution using the definition of convolution. So if we consider y star sin t, then we have 0 to t y of u sin of t minus u. Therefore this integral is nothing but convolution of y and sin t. So this will be the first step in the solution of integral equation. If we are able to write down this integral as a convolution of two functions, then only we can apply this method. So this is the first step. After that we consider Laplace transform on both sides of this equation, and we will have Laplace transform of convolution here. So here we will apply convolution theorem for Laplace transform, which says that Laplace transform of convolution equal to product of Laplace transform of those two functions. And then we use the notation y bar s for the Laplace transform of unknown function y, and we try to find out y bar s by simplifying all these things. And once we obtain y bar s after simplification, we consider inverse Laplace transform of y bar s, and we obtain the unknown function y of t, which is the solution of given integral equation. So remember, this is very easy method. We just have to write down our integral in the integral equation in terms of convolution of two functions. This is main step, how to write down, or whether it is possible to represent given equation as a convolution of two functions. Once you write this integral as a convolution of two functions, then things are easy. You have to first apply Laplace transform, and you will obtain y bar, that is Laplace transform of y of t. And to obtain y of t, we have to find out inverse Laplace transform of y bar. So those things are familiar to us. The only new thing is write down the integral as a convolution of two functions. Okay, fine. I stop here. In this lecture, we have discussed how to solve certain type of integral equations using Laplace transform. So this is all about this session. I hope you like it. Thank you very much.